Given, the root of a binary tree, not necessarily a search tree, and two distinct nodes P and Q that both appear in the tree. Return, their lowest common ancestor, meaning the deepest node that has both P and Q in its subtree, where a node counts as a descendant of itself. Constraints, between 2 and 10 to the 5th nodes, all values are unique, P is not Q, and both nodes exist. Example 1, P is the node with value 5 and Q is the node with value 1. They live in different subtrees under the root 3, 5 is under the left child and 1 under the right, so the lowest common ancestor is 3 itself. In a plain binary tree, values do not tell you which branch to take. You recurse from the root into both subtrees, that is the search party. On screen, short flashes run along links downward from the root and a step deeper, standing in for that blind exploration until a node actually meets a target. When recursion lands on P, that call returns P as the answer for its subtree, no need to hunt below P for P again. We show a pulse climbing from 5 up toward the root along the parent edge, a ping that says this side found one of the targets. The lowest common ancestor is the shallowest node where the left and right subtrees each hand back a non-null result for this pair. Here, the left side eventually supplies 5 and the right side supplies 1. When both reports meet at the same node, you have found the split point, that is the lowest common ancestor. Post-order depth-first search, we label each node after its subtrees. Each ret badge is what the classic recursive call returns from that subtree for P and Q. The walk order is post-order for clarity, the code checks P and Q before recursing. Example 1, P is 6 and Q is 4. That visit is P, 6 is one of the two targets. That visit is Q, 4 is the other target. This is the moment, both recursive calls return a real node, so the split is here. This node is the lowest common ancestor, not just passing a pointer through. The root's return value is 5, the lowest common ancestor of 6 and 4. Ancestors above the LCA simply relay that same node upward. Same tree, P is 5 and Q is 4. Here P is an ancestor of Q, so the lowest common ancestor is 5 itself. The walk only touches nodes the recursion actually visits, nothing under 5 besides 5 itself. That visit is P, 5 is one target, 4 lies in its subtree. The lowest common ancestor is P itself, 5 is on the path from the root to 4. The code hits the base case at P and returns immediately, so it never recurses into the children of P for this search. That is the early exit. Again the answer at the root is 5, one target is the ancestor of the other, so that ancestor is the lowest common ancestor. Let n be the number of nodes and h the height of the binary tree. Time is O of n in the worst case. One depth-first search visits each node once, with constant work to combine left and right results. Space is O of h for the recursion stack, since call depth follows the height of the tree. If the tree is skewed, h can be about n, so worst-case stack space is O of n. We do not need an extra hash map or queue beyond that stack. Function lowest common ancestor, we receive the current subtree root and the two nodes p and q. If the root is null, or the root is p, or the root is q, we stop here. This is the base case. Return the root, one of the targets is already at this node, or the subtree is empty. Otherwise recurse on the left child and store the result in left. Recurse on the right child and store the result in right. If both left and right return a non-null node, the split is here, so this root is the lowest common ancestor. Return this root as the answer for the whole subtree rooted here. If only the left side found something, we relay that pointer upward. Return left. Otherwise return right, which may be null if neither subtree contained p or q below this root.